Hello, everyone. Come on in. Come on in. Anybody have any questions while we're waiting? Looks like everyone's here now or getting here. Boy. All right. Well, we've got 13 of you now. I think there's supposed to be 16 in the classroom, so that's not horrible, I reckon. What we have left to talk about is basically the energy in a wave, the power in a wave, also something that we sort of call the intensity of a wave, which is the power per unit area. So those are some things we need to talk about on waves, and they're pretty straightforward to come by. So I'm going to show you that. And then I'm going to give you the actual wave equation, a wave equation that occurs in many different fields. Your book derives it, I think, for a string, a wave on a string. I'm not going to go through the problems of deriving it. It's actually pretty straightforward to derive, but it's actually pretty straightforward to derive, but your book does a good enough job. I think y'all can follow if you want to. But one of the things you're supposed to be able to learn here, like I said, is be able to apply knowledge that someone's given you, and that's what the textbook is doing right now. Some of this is the actual approach to getting the wave equation, the actual approach to deriving these velocity equations and stuff like that. That's a little higher grade than what we're expected in the calculus-based physics course, in the calculus-based physics course. I want to double check something too. I just looked at our notes. I want to make sure. Oh yeah, so I did describe the moduli last time, so I wanted to refresh you on that just a little bit. So remember, I told you moduli are stress over strain, and I reminded you that the word stress, S-T-R-E-S-S, has a R-E-S-S in it, just like pressure has an R-E-S-S in it. So I want you to use that to remind yourself that the stress part is one that has like a force over something. Okay, in this case, for instance, in the bulk modulus, it's force per unit area. Or also in the case of a wave traveling along a rod, we ended up using the elastic modulus, and in that case, it was also force multiplied by the cross-sectional area over which the force was supplied, and that surface was actually perpendicular to the force. Okay, so that's just like pressure. So that's why it's okay to call it pressure. And that's the norm. But there's another modulus I wanted to discuss with you that's actually super relevant when we're talking about shear waves. And this is something that we had to do, for instance, when I was in structural engineering. A lot of people want windows at the corners of their houses. That's a surprisingly difficult thing to put on a house, a wood-built construction house, because basically your corner has your stress, your shear stress on it. And in order to deal with that, you have to put these thrusters in there, which are things that deliver the shear stress away from the corner to a shear wall. And then that shear wall has to, meet certain criteria, or else the house is going to rack. And that's a problem. You obviously don't want your house not shaped like a square solenoid anymore, or square, I think they call it a prism, square prism anymore. And that's what happens if the shear is going off. It's basically the top part was moved this way while the bottom stays perfectly square. So they make these shear walls. In fact, you can buy them just like you can buy Simpson hangers for hanging rafters and tie downs for keeping the rafters from flying up in a storm. Simpson actually sells shear walls as well. So they literally will build a 4-foot wide or even 6-foot wide section of wall with 2x4s and OSB plywood, and then they have like nails every 6 inches on every all around the edges, and sometimes even during the middle, to make sure the shear strength is strong enough. So I thought I'd introduce that shear modulus and then go into the energy. So let me turn on my document cam. Before I do, anybody have any questions? No one's asked anything yet. I think I got all the tests categories corrected. I think all the dates of the chapters are fine. I sort of forgot about us only having class Monday, Tuesday, and maybe Wednesday of next week. I'm not sure about Wednesday. I need to check that. But because of that, there's gonna that cuts out some of my time. So ideally, I'll do 17, or excuse me, chapter, we just finished 15. Ideally, we will be finishing 15 today, and then next week I'll start into chapter 43 on elementary particles. So I'm not sure I'll be able to finish it by then, but that's what we're doing. So let's go ahead and turn on the document cam. No questions, right?
I'm okay.
Yeah,
Go for it, Brandon or Jacob.
I noticed that I believe most classes on like Wednesday are canceled because I think that's the start of break.
Yeah, that's
So
what
I
I noticed.
noticed-
I hadn't checked it, but yeah, I think you might be right.
I also saw that we have something due Wednesday and the Sunday we're on break.
Yeah, I think I'm gonna push those back just because I was forgetting they were break days. So now that's gonna be a problem though, because what I'll do is I'll push the Wednesday and Sunday over Thanksgiving break. I'll push all to Wednesday. So that Wednesday might end up having a buttload of stuff due. So just, don't wait till Monday to do it, or you're gonna be in trouble.
So you're saying you're gonna push it to the Wednesday of the next
we-
week.
Yes, after no, the Wednesday of the week after Thanksgiving.
Yeah, okay. Yeah, I just want to make everyone stressed out about having work to do over break.
Yeah, exactly. I want you guys to have a break too. I mean, I think you should still read physics book every day just because it's awesome stuff to do, but I don't expect anybody's really going to listen to me on that one. I read a physics book every day. Actually, I read several physics books every day. All right, so the shear modulus, remember, just in general, modulus is defined to be stress, which again, I'll underline the rest, over strain. And strain, I hope you think, is about something that's screwing up the geometry. So this one's force related and this one's geometry related. And what I mean by geometry related, like you're screwing up the shape of the object. So I thought I'd introduce shear stress. And I think the symbol that just about everybody uses is S, or the shear moduli, excuse me. What you can imagine here is a force. I forgot to put date. What you can imagine here is a force applied to a wall or any object whose length perpendicular to that force is L. So this is the force. And what's going to happen is the wall is going to rack and be shaped like that parallelogram now. This distance from here to here is delta L. So the shear modulus is the force divided by that length over the delta L divided by that length. So that's the shear modulus. That's one that comes in pretty handy. Like I said, this is a lot of what I had to do when I did structural engineering. We had some people that worked with us that had never done wind analysis, and that was the thing I taught myself to do, which is why I got the job in the first place. Being a physicist with no real engineering experience other than what I've read and taught myself. So I came in and I immediately started doing wind analysis. Of course, we're on the Outer Banks, so you kind of wonder why the other people that were working weren't doing wind analysis. Working literally probably 20% of our jobs were in Hatteras, which has a 150 mile per hour wind zone. So anyways, you have to calculate the pressure on a wall due to winds following this ASCE 798 publication. And you do that calculation, you get a certain pressure per square foot, and then you got to account for that pressure going all the way down to the foundation. And a lot of times you had to have shear walls, and this is a type of formula we would use for that. So anyways, I think that's kind of interesting and something to keep in mind. The moduluses are really where engineering or physics goes into engineering, is because basically that's where you have to stop just taking your highbrow physics principles and start taking the data that the engineers has given us. And that's stuff like shear modulus, elastic modulus, and bulk modulus. Now, the other thing is the energy of waves. Now, we saw before that the energy of a harmonic oscillator was basically either 1/2 Ka squared, because that's when the energy was a total potential energy, or 1/2 mv squared, because that's when the energy was total kinetic energy. Well, we're going to take off from there and say energy is equal to 1/2 Ka squared. Okay, that's the total energy, no ifs, ands, or buts about it, and that's actually right. So you can immediately see that the energy of a wave is proportional to the square of the amplitude. So don't forget that's amplitude. Now, if you remember correctly, we had omega is equal to 2 pi times f, and we also had that omega was equal to the square root of k over m, so that f, which is 1 over the period, would equal, in fact, or excuse me, 1 over the period. I don't know why I wrote pi. 1 over the period. We would write that as the square root of k over m times 1 over 2 pi, right? Well, if you square that, you get f squared is equal to 1 over 4 pi squared times k over m. So you can solve that for k and eliminate the k, because what the crap's a k in the wave equation? We don't know that, but we do know the frequency is related. So I'm trying to get a relationship to get that k out of there so I can be more dealing with wave type stuff. So the k is going to be 4 pi squared m f squared. 4 pi squared m f squared. Yes. So now I can take this and say the energy of a wave is equal to 1/2. Now I'm going to take that and multiply it by 4 pi squared m f squared. That's the k, times a squared. So we can actually get that the energy of the wave is equal to 2 pi squared m f squared a squared. So you see the energy of the wave is directly proportional to f, the frequency squared, and it's also directly proportional to a squared. Now, if you wanted, actually, I was thinking about something else. Hold on. Okay, so yeah, if you want to think about this in terms of mass, we can't really talk about the mass of a wave, but we can sort of talk about the density of the material through which it's traveling. So if you imagine that a wave is traveling like this, and you take a little box, say, and you imagine that box has a surface area S, then you know the length of that box, L, is going to be given by the velocity of the wave times delta t. So now we can say, well, the energy of the wave, since mass, or since density is equal to mass over volume, we can get rid of the mass by multiplying density times volume. So I'm going to say E is equal to 2 pi squared. Now, in place of m, I'm going to put the density of the material, and then I'm going to multiply that by the volume, which should be V delta T times S, where S is a surface area. So you see that whole thing right there is the volume of that little box that I made. Okay, and now I still have the F squared A squared. So that's actually our final expression. I'm going to say energy is equal to 2 pi squared. Let me put it in the same order that I normally do. We normally do 2 pi squared rho then I do S, and then I do V times, instead of delta T, let's just call that T. Sorry about that. I was remembering my relativistic stuff where I was using delta T, and I just instinctively used delta T. So we're just going to change that from delta T to T, to just plain T. And when we do that, we get S times V times T times F squared times A squared. So if they ask you for the energy carried by a wave, this is a formula you now can use. Okay. I more or less derived it from an argument about how it should be like a simple harmonic oscillator. And it turns out experimentally it's right. You can see the energy of the wave depends on the density of the matter through which it's traveling, if it's actually traveling through matter. There's a whole different thing when it travels through a vacuum, which we worked out in the 242 class. Then the velocity of the wave is directly proportional to that. So that means if the wave is going faster, it's bringing more power. It's proportional to the square of the frequency and the square of the amplitude. Now, we can now get the power, because the power is basically the energy per time. So power of a wave is equal to energy per time, at least on average. So we can say the average power should be equal to 2. Notice we already had the T in there. That's why I went ahead and changed it. So I can just put a T down here. 2 pi squared rho S V F squared A squared. So that is actually the power in a wave. And also you might want what we call the intensity, which is the power per unit area. In other words, an area perpendicular to the plane that the wave is hitting is the area we're talking about. So that's that S right there. So if I divide out the S, then I get I, the intensity, which has units of watts per square meter, by the way. I, the intensity, is now 2 pi squared rho V F squared A squared. And that's kind of helpful because what you know is, for instance, you know that let's say, for instance, in the case of gravity, we had a point particle, say right here, and right here would point radially inward a vector.
Hey, sir, quick question. What was A again?
Oh, that's the amplitude of the wave.
Oh, that's right. Yeah, you mentioned S being area, and I got that. I mixed up there for a sec. Thank you.
Gotcha. No problem. So if you remember Newton's second law, or Newton's law of gravity, G m1 m2 over r squared, where this say is m1 and this say is m2, then in that case you see that basically the force right here is inversely proportional to the square of the distance between them and stuff like that. And you also see that this sort of force radiates out in every direction. Okay. Well, that's exactly the same thing that happens with waves coming from point sources, is they go out an equal amount in every direction. So from that, you can see that, okay, well, if I have this and I have a wave traveling out this way, like so, then when I get out to here, I might have a power, or excuse me, an intensity equal to power divided by, let's say, 4 pi r1 squared. But then if I go out here to say r2, which equals 2r1, then you get that same amount of intensity is true, because that's the total intensity the thing can put out. But now it's that same power divided by 4 pi r2 squared, but r2 is equal to 2r1. So you see that basically the intensity at 2 meters is 1/4 of the intensity at 1 meter. So what we get is evidently this intensity falls off like 1 over r squared. So I made mention before to you guys about Einstein saying when he became super famous because of his general theory of relativity predicting the bending of starlight, people started asking them questions about everything. They asked them questions about the Israel issue because, you know, this was right around the end of World War I. And they asked him questions about politics. They also asked him about ESP and telekinesis. And he said, if you show me that it obeys a 1/r² law, then I'll believe it. And this is exactly why he does that, is whenever you're talking about an object that's small compared to the distance away, then that object's going to act like a point source. Therefore, you expect its abilities to fall off as 1/r². So that's just another neat little thing to remember about waves. So you can actually use that. For instance, your book does a calculation of earthquake intensity as a result of that. So that's something you can do. But now that's just pretty straightforward, blatant, what we call plug and chug problems. So I want to get into the wave equation and explain to you what that is, and then give you the solution for it. I'm doing it in a different order than your book does. Your book sort of gives you the solution and then later on derives the actual wave equation. I'm not going to derive the wave equation at all, but I will tell you that the wave equation is the second derivative of some quantity d. Now, this generally means like the amplitude or something like that with respect to x. So we take two derivatives with respect to x, and then that's equal to 1/the velocity of the wave squared times the second derivative of the amplitude function t squared. That's the wave equation. And it has partial derivatives. So it's actually a partial differential equation, not a ordinary differential equation. So it's a little bit bigger than your normal scenario where you're just doing dd over dx or something. This is basically what you're doing is you're pretending that this function, which actually might be a function of say x, y, z, and t. It's normally just x and t, by the way, but it could be all those things. Then you're pretending like all the other constants, the y, z, and t are constant, or all the other variables, the y, z, and t are constants, and you're taking the derivative of it with respect to x, with playing that role. So that's the actual wave equation. So whenever you see a second order derivative in space equal to some number times the second order derivative in time, that number is 1/the square of the velocity, and this is a wave equation. Okay. Well, it turns out this is linear. So if I do something like, let's say D1 is a solution to the equation above, and D2 is. So let's see if A1 D1 plus A2 D2 is. Okay, so what I'm going to do is I'm going to take the second derivative with respect to x squared of A1 D1 plus A2 D2. So these A's are supposed to just be constants. This is called a linear combination. And any things that take a linear combination and spit out individual separate parts, just like they had before, is called a linear operation or a linear operator. So when I take the derivative of this with respect to A1, that's just a constant. So I get A1 times the second partial of D1 with respect to x squared plus A2, which is just a constant again, times the second partial of D2 with respect to x squared, right? Well, I already know D1 is a solution. Specifically, the second partial of D1 with respect to x squared is equal to 1/v, let's call it V1 squared, second partial of D1 with respect to time squared. So I can replace that and say that's A1 times 1/V1 squared, second partial of D1 with respect to x squared, or with respect to time squared. Okay. Similarly, the other one's going to be A2 times the second partial of D2 with respect to t squared. Oops, and I left the 1/V2 squared off. Okay. So from that, you see, yes, clearly, because I can group these A's, and over here I'll get just A1 basically is A1 is equal to D2 squared plus that. So you see that automatically this is solved. So now we can see that this equation, this wave equation, is what we call a linear equation. And anytime you find a solution to it and another solution to it, you can add those two solutions together and even multiply them by an arbitrary constant, and you'll still get a valid answer. That's sort of the essence of the superposition principle, which just says, hey, all you have to do is just take the functions and add them together, and that'll give you the right answer. So that's where this linear superposition, or this, excuse me, the superposition principle comes from. Now that I have that, I need to show you what the actual solution to it is. And there's a lot of different ways you can actually write it. You could use cosine, you could use sine, you could actually use the sum of sines and cosines, all sorts of cool stuff. But what I'm going to do is, just like we had omega equals 2 pi f, but that's equal to 2 pi over the period. So the period is sort of the length of the wave in time, right? That's the period from here to here. Similarly, in space, you have the length of the period as the wavelength, right? So it seems reasonable, since we have a omega equal to 2 pi over t. We used to use that, in fact, for simple harmonic oscillator. We said that x is equal to a cosine omega t plus phi. So it stands to reason, since a wave is a repetition in space and time, then we sort of need something like that, but for space. And lo and behold, we define k to be 2 pi over lambda, just like omega is 2 pi over t, k is 2 pi over lambda, and that's our answer. We're going to say x, the answer to the wave equation, is some constant a times the cosine of omega. Well, actually, let me put it in a different order. I'm going to do k times x minus omega t, and then I'm going to add a phi to it. So that turns out to be exactly the solution. You can pull that, throw that in there, and you'll find that actually the velocity ends up being lambda times f, which we already knew. But in terms of these new parameters, it's just omega over k. As you can see, that would be 2 pi over the period divided by 2 pi over the wavelength. So you'd end up getting wavelength over period, which is wavelength times frequency. Any questions on that? All right. Oh, I'm getting sick and I don't know what's going on. That's not good. Hold on a second, everybody. All right. So with that, you can do all sorts of cool stuff, and you can realize, for instance, this wave is actually moving to the right. This whole thing, the argument of a sine or cosine making up a wave, is always called the phase. And it's sort of like the snapshot. You can see a whole wave and represent it by that. And then you say, okay, well, if I kept that constant, then what I'm looking at is just this wave, and I'm going to see what happens over time. So when I do that, I'll say constant, let's call it C equals a constant. Then I'll say C is equal to KX minus omega T. If I want to keep that a constant, then what that means is K times X is equal to C plus omega T. And you can see as T gets larger and larger, then we get this constant plus a number. So in other words, this means it's a right traveling wave. Okay. Now, if you did the same thing for, let's say C2 equals KX plus omega T, then you would get KX is equal to C minus omega T. And as T goes up, we see the X goes down. So this is a left traveling wave. So those are the big principles you need for this. And I'm sorry, I'm going to have to call it because I'm getting ready to throw up or something here. I don't know what's going on, but those of you who have me for lab, just plan on being there for lab. We've actually finished chapter 15 anyways. I've covered all the major topics. I just haven't worked as many examples as I'd like. So please look over the examples in chapter 15. Make sure you can do all those as sort of the low-hanging fruit. And I will see you guys either in lab or I will see you Monday. I am sorry, I got to go. Oh, thank you, Brandon. Oh boy, I feel horrible.